Welcome to This Explainer. Today, we're taking a seriously fascinating journey. We're going to start right from the microscopic wonders of your very own eye and travel all the way up to the grand, colorful mysteries of the sky above us. We're talking about exactly how we perceive the world and, honestly, why it looks the way it does. Let's get into it. So think about this for a second. Right now, at this exact moment, you are actively operating the ultimate biological camera. Yeah, the most complex, high-definition camera in the world isn't sitting in your pocket on your phone, it's right there in your head. The human eye is easily one of the most valuable, wildly sensitive sense organs we have. It's the whole reason we get to experience this beautiful, colorful world, and it actually works remarkably like a highly advanced camera system. If you think about how a camera works, the eye is basically doing the exact same thing. Light first enters through this clear front window called the cornea. That's where most of the light bending happens. Then you've got a muscular diaphragm called the iris acting just like a shutter, regulating how much light hits your pupil. And finally, the crystalline lens fine-tunes the focus. It projects a real inverted image right onto the retina at the back, which then instantly fires electrical signals straight to your brain. Pretty amazing, right? Now, unlike a rigid glass camera lens, your eye's lens is made of this flexible, kind of jelly-like material. And this flexibility allows for an absolutely wondrous biological feat known as the power of accommodation. Basically, your ciliary muscles are constantly working behind the scenes to modify the lens. When those muscles relax, the lens thins out, increasing its focal length so you can spot distant objects. But when you look at something up close, the ciliary muscles contract, the lens gets thicker, the focal length drops, and boom, that nearby object comes into sharp focus. But, there is a limit to this amazing flexibility. The focal length of your eye lens literally cannot decrease below a certain minimum limit. Try grabbing a printed page and holding it closer than 25 centimeters to your face. The text is going to blur, and you're definitely going to feel some eye strain. That's because 25 centimeters is the absolute near point of distinct vision for a young, normal eye without causing strain. So for a normal eye, you can see clearly anywhere from that 25 centimeter mark all the way out to infinity. But what happens when this brilliant lens system loses its flexibility? Well, as we age, or if the actual shape of our eye changes, we can gradually lose this power of accommodation. And this leads to three main defects. First, myopia, or nearsightedness. Then, hypermetropia, which is farsightedness. And finally, presbyopia, which usually happens as our ciliary muscles just naturally weaken over time. Fortunately for us, spherical lenses offer a pretty clever fix for all of this. To picture this mechanics, think about a myopic eye. An elongated eyeball causes the image to focus just in front of the retina, which we can easily correct with a concave lens to push that focus back where it belongs. On the flip side, in a hypermetropic eye, the eyeball is actually too short, causing the light to focus behind the retina. We fix that by using a convex lens, giving it that extra converging power to bring the light into perfect focus right on the retina. It's essentially biohacking with glass. It is so incredibly easy to take our highly complex vision for granted. We just open our eyes and the world is there. But this beautiful poem by C. Cibber really reminds us that not everyone gets to experience the colorful world we're about to explore. It kind of forces us to pause for a second, right? To just appreciate the immense, literal gift of sight. And that actually brings us to an incredibly powerful realization. Did you know our eyes can live on even after we die? By simply choosing to be an eye donor, we can pass on this gift. The statistics here are just staggering. Out of the 4.5 million people with corneal blindness who could be cured right now through a transplant, a heartbreaking 60% are children under the age of 12. The removal is a straightforward 15-minute procedure, causes zero disfigurement, and incredibly, just one single pair of donated eyes can restore the miracle of sight to up to 4 people. It quite literally brings light back into their lives. Okay, let's zoom out a bit from our own anatomy. We've talked about the biological camera, but let's look at the physical universe it's actually recording. We are constantly surrounded by light, but what exactly is it? To answer that, we have to travel back to a legendary discovery made by none other than Isaac Newton. So Newton was the very first person to use a glass prism to obtain the spectrum of sunlight. He discovered that passing sunlight through a triangular glass prism causes dispersion. Basically, the prism splits that seemingly invisible white light into a breathtaking 7-color spectrum. Because different colors of light bend at slightly different angles as they pass through the glass, it creates that distinct band of colors we easily remember with the acronym VIBGYOR, that stretches from violet, which bends the most, all the way down to red, which bends the least. Now, what is truly mind-blowing is that nature does this exact same thing, just on a massive scale. Have you ever wondered where rainbows actually come from? Well, right after a rain shower, there are millions of tiny water droplets just suspended there in the atmosphere. And every single one of those tiny floating water droplets is acting as a natural miniature prism. Nature actually follows a very specific three-step recipe to bake a rainbow. First, as sunlight enters the tiny raindrop, the droplet refracts and disperses the incident light into its component colors. Second, those separated colors hit the inner back wall of the raindrop and internally reflect. Finally, the light refracts one more time as it exits the raindrop, sending that gorgeous spectrum directly into your eye. So a rainbow is really just massive atmospheric dispersion combined with internal reflection. Okay, moving from the daytime sky to the night sky, let's look at another spectacular natural phenomenon. Have you ever stared up at a clear night sky and wondered why the stars are constantly flickering and dancing around like tiny candles, while the planets remain totally, solidly steady? The answer lies in a little thing called atmospheric refraction. You see, our atmosphere is this turbulent, constantly shifting mix of hotter, lighter air and cooler, denser air. Because stars are unimaginably distant, they act as tiny point sources of light. As their starlight passes through our chaotic atmosphere, the path of the light varies slightly, bending back and forth. This makes the apparent position of the star fluctuate, and the amount of starlight hitting your eye actually flickers, hence twinkling. Planets, on the other hand, are much closer to Earth, so they act as extended sources of light. If you think of a planet as a large collection of point-sized light sources, all those random flickers from individual points just average out to zero, completely nullifying the twinkling effect. And atmospheric refraction is so powerful that it actually plays a visual trick on you every single morning and evening. Because the atmosphere bends light towards the normal, it literally bends the sun's image over the horizon. This means you actually see the sunrise a full 2 minutes before the sun physically crosses the horizon. And yep, the exact same thing happens at dusk. You keep seeing the sun for 2 full minutes after the actual sunset. Crazy, right? Let's bring it a bit closer to the ground now and look at the interplay of light and particles in our air. Our atmosphere is this messy mix of smoke, water droplets, and dust. When a beam of light strikes these fine particles, it scatters, which suddenly makes the actual path of the light visible. We call this the Tyndall effect. You've definitely seen it, like whenever a dusty room is lit by a single sunbeam peeking through the blinds, or when sunlight breaks through the misty canopy of a dense, humid forest. So the crucial takeaway here is how the size of these scattering particles affects the colors we see. The molecules of air and fine particles in our atmosphere are smaller than the wavelength of visible light. Because of this, they are incredibly effective at scattering shorter wavelengths like blue light, but they are terrible at scattering longer wavelengths like red. In fact, red light has a wavelength about 1.8 times greater than blue light, so the red light just passes straight through the fine particles completely undisturbed. And by the way, this is exactly why danger signals are painted red, so they can pierce right through thick fog or smoke without getting scattered away. All of this builds to an astonishing realization about our daily lives. Since the fine particles in the air scatter the shorter blue wavelengths so strongly, that scattered blue light bounces all around and enters our eyes from every conceivable direction. That is what creates our beautiful blue sky. But what happens if you leave the Earth's surface and fly incredibly high up in a rocket? Well, if you're an astronaut flying at very high altitudes, the sky actually appears completely dark. Why? Because there's no atmosphere up there. Without the air molecules and fine particles to scatter the sunlight, there is no blue canopy. The light just travels straight on. The vibrant blue sky we live under every day is essentially a spectacular optical illusion caused by the scattering of light by the very air we breathe. So, the next time you step outside, I really want you to think about this. When you gaze up at a dazzling sunset, or spot a rainbow after a heavy storm, or honestly even just sit down to read a good book, ask yourself, are we just incredible biological lenses, constantly and silently decoding a wondrous universe of scattered light, shifting atmospheres, and hidden prisms? I hope this explainer has changed the way you see the world around you. Thank you so much for joining me on this colorful journey of understanding.